Right. This set of slides will deal with Gibbs energy and equilibrium. So our objectives will explain how temperature affects spontaneity. We'll relate standard Gibbs energy changes to equilibrium constants. So as a reminder, if Gibbs energy is negative, it's spontaneous. If Gibbs energy is positive, it's non-spontaneous. Gibbs energy was defined as delta G is equal to delta H minus T delta S, where delta G is Gibbs energy. Again, greater than 0 is non-spontaneous, less than 0 is spontaneous. Delta H is enthalpy, greater than 0 is endothermic, less than 0 is exothermic. T is temperature in Kelvin, and entropy, you will have less disorder if it's less than 0 and more disorder if it's greater than 0. So we're going to go through here and consider the mathematical relationships that we've got. So if enthalpy is greater than 0, which means it is endothermic, and we have an entropy that is less than 0, meaning there's less disorder, then when we put these two values together in our delta G equation, positive minus a negative, meaning a positive, positive plus a positive is always positive, and since delta G when it's positive is non-spontaneous, there is no way, no situation in which you have an endothermic reaction where you're tending toward less order, where you can actually have a spontaneous thing. That's right. The system is always positive when you have an endothermic reaction and you have decreasing entropy. All right, now let's try another case. What about the situation where we have an exothermic reaction and our entropy is increasing? So exothermic entropy increasing. So our delta H is negative, our delta S is positive, the negative of positive is negative, so negative number minus a negative number, this will always be spontaneous every single time. So if you have an exothermic system with increasing entropy, it will always be spontaneous. Now, the next two cases are the in-between. What about an endothermic system in which entropy is increasing? In this case, sometimes you'll end up with a positive number, and sometimes you'll end up with a negative number for Gibbs energy, depending on the temperature. So if the temperature is high, it will be spontaneous, because at high temperatures, the entropy will increase to overcome the positive enthalpy change. Right, so if delta S is positive, the minus T delta S is negative. If it's large enough, it overcomes delta H. So even if you have an endothermic reaction, if it increases the entropy of the system enough at that temperature, it'll still be spontaneous. There we go. So spontaneous when the temperature is high, non-spontaneous when the temperature is low. So we have one more case to consider. What if we have an exothermic system with decreasing entropy? So in this case, we're starting with a negative number for enthalpy and subtracting a negative entropy, which means that value will be positive in the equation. When the temperature is low, the process will be spontaneous, but otherwise it will be non-spontaneous. Okay, so where we have an exothermic reaction with entropy decreasing, only favorable at low temperatures. Now the book summarized these findings in a different table. Personally, I never memorized any of this. I just always picture the math in my head and then I know what's going to happen. But use whichever version of this you find more helpful. Okay, moving on. We can use standard enthalpy and entropy values to calculate the Gibbs energy. So we need to find the change, determine the temperature at which the phase change becomes spontaneous when we go from P4 solid to P4 gas. And I have some standard values that I've looked up in the textbook. All right, so we're going to plug it into the delta G equals delta H minus T delta S equation. But first we need to figure out the delta H and the delta S. So we're going to do final minus initial. And when we do that, we get 58.91 kilojoules per mole for delta H and 115.6 for delta S. So this is an endothermic reaction that is increasing the entropy of the system. So spot check, does this make sense? To go from a solid to a gas, you have to add energy, so it should be endothermic. In order to go from a solid to a gas, you have increased the entropy of the system by quite a bit, and that is positive. Okay, so yes, these are the expected things. Now, in this case, we know that at some temperatures, it will be non-spontaneous. In particular, we know that we need to be spontaneous at high temperatures. We just talked about that. So let's find our threshold. Where does that switch take place? If we put delta G equal to 0, okay, so that'll be at equilibrium where both changes can happen spontaneously. We're going to plug in 0 for delta G, and then we're going to solve for T. Okay. And when we solve for T in this equation, we get 509.6 Kelvin. And we know that at high temperatures, this is spontaneous, so it will be spontaneous above 509.6 degrees. Now, this is our second gut check. Does that make sense? Above 509.6 is pretty hot. We expect to go from a solid to a gas spontaneously at higher temperatures. We've seen this on lots and lots of different phase diagrams. Gases exist at higher temperatures, so yes, this checks out. Now, let's talk about non-standard Gibbs energy. We just said that Gibbs energy is equal to 0 when the system is at equilibrium. That is its definition. But what happens when we're at a non-standard condition? If we don't have this, we have the standard table, but we're at a non-standard temperature. There's a mathematical relationship defined by Gibbs energy at the non-standard condition, so it's just plain old delta G, and that's equal to delta G standard plus RT natural log of Q, where R is the ideal gas constant, T is temperature in Kelvin, and Q is the reaction quotient. All right, so let's try an example problem to make a little bit more sense of this. Calculate the Gibbs energy change for the following process. So we have 2 ammonia gas decomposing into hydrogen gas and nitrogen gas with a delta G of 33.0 kilojoules per mole. We are given a temperature of 25 degrees Celsius, a pressure for nitrogen of 0.75, pressure for hydrogen of 0.15, and a pressure for ammonia of 11.5. All right, so looking at this, we've got a couple things to do. First off, you may be a little bit confused. Delta G standard, why wouldn't 25 degrees be standard? That's what it is in my book, and you're right, it is. But you can have delta G standard for different temperatures. I grabbed this from a book where delta G standard was for 0 degrees Celsius. So it changes when you go to 25. Standard enthalpy, entropy, or Gibbs energy values can be at any temperature so long as you specify which one it is. There are tables for 0 degrees Celsius, for 25 degrees Celsius, for biological conditions. All of those are common to be able to find. Anyway, back to the regularly scheduled program. So looking at this problem, we need the Q expression in order to use this equation. So we think back to that chapter on equilibrium, and we define our Q equation. All right, and in our Q equation, we have products over reactants, and we use the coefficients as exponents in the equation. Temperature has to be in Kelvin, so we need to convert this 25, and we get 298 Kelvin. And at that point, we have everything we need to plug all the things in. Now, I will warn you right now, our Gibbs energy here is given in kilojoules per mole, and I have given you the ideal gas constant in joules per Kelvin, so you need to convert it into kilojoules per Kelvin mole, which is what I did. And then I just plug things in, right? I just plug plunked those values into all the things. And when I solve, I get 6.1 kilojoules per mole. So again, we ask ourselves the question, does this make sense? This process goes from 2 moles of gas to 4 moles of gas. So entropy in this case, definitely positive. We're getting more moles of gas. That is way more chaos. It is not necessarily clear straight off what enthalpy will be. So there are 2 options for temperature dependence when entropy is positive. If we have an endothermic reaction, the Gibbs energy will be negative and therefore spontaneous when the temperature is high. If we have an exothermic reaction, the reaction is always spontaneous. So in this case, it must be endothermic based on the fact that the standard Gibbs energy that's reported is positive. We increase the temperature and the Gibbs energy is less positive. So at higher temperatures than 25 degrees Celsius, it will become spontaneous reaction, right? High T will lead to it being spontaneous in this case. All right, moving on. All right, so we've now related Gibbs energy and reaction quotient. At equilibrium, Q is defined as K. If we're dealing with standard values, then we can get rid of that extra delta G, and we solve, and delta G standard is equal to negative RT natural log of K. So let's look at how this relates to kinetics. If K is greater than 1, then when you plug it into the equation here, delta G equals negative RT ln K, natural log of K will be greater than 1, and the overall reaction will have delta G as negative. So if the products are more abundant than reactants, then it's spontaneous. This makes sense because the forward reaction is favored. Then you would expect there to be more reactants, or sorry, more products proportionately. Yay, it makes sense. All right, so now let's look at the case where K is less than 1, and in this case the reactants are more abundant, so you would be thinking that your reverse reaction is faster. If you plug in the value of less than 1, natural log of K will be negative, and a negative of a negative is a positive, so Gibbs energy will be positive, and that is non-spontaneous. And finally, we have one last case where reactants and products are equally abundant, and the natural log of K is equal to 0 when K equals 1. All right, it is very unlikely that your delta G will be equal to 0. That would only happen at a very specific temperature for any given system. And it can be both spontaneous and non-spontaneous, depending on the temperature. So that's how you find out. All right, let's try an example equation or an example calculation using this relationship. So we're going to calculate the KSP of the following dissolution reaction using Gibbs energy. We are given the reaction. We have silver bromide separating into silver and bromine ions. We have a KSP equation that we were given, and we have standard Gibbs energy values that we have been given. We are recalling that delta G standard is equal to negative RT natural log of K. So what do we do? The first thing we're going to do is determine our delta G standard for the reaction. We're going to treat it the same way that we do entropy, enthalpy, etc., products minus reactants. And in this case, we don't have to worry about multiplying by moles because they're all 1. So when you put that together, products minus reactants, you get 71.19 kilojoules. Now, this is a standard temperature or standard value, and since most tables are at 25 degrees Celsius, if I don't specify, assume that that is what we're doing. So this is for 298 Kelvin. We're going to plug it in. We're going to plug it into our delta G equals negative RT natural log of K, and we're going to solve for KSP. So we first get everything onto one side of the equation and equals KSP. So natural log of KSP is equal to negative 28.734 moles, because that's the units we have left. We're going to take E to both sides, and when we do that, our KSP is equal to 3.31 times 10 to negative 13th. Now, you may be having a little pause in your brain. Wait a second. Why did we suddenly have no units? Because we had moles in there before. It's true. We did. But when we put anything to an exponent or take a log of it, we drop the units. It's more convenient to do it this way, but also we normally try to get rid of the units before we do this thing. So there you go. That is the KSP of silver bromide. To summarize, delta G is equal to delta H minus T delta S. It is also equal to delta G standard plus RT natural log of Q. Now, whether or not something is spontaneous depends on your delta H, delta S, and your sign, right? So delta G, when it's negative, is spontaneous. We will be spontaneous if we have an exothermic reaction increasing in entropy, and that will always be spontaneous. If we have an endothermic reaction decreasing in entropy, it will always be non-spontaneous. And if we have an endothermic reaction that increases entropy, it will depend on the temperature. The process is spontaneous at high temperature. Finally, if we have an exothermic reaction that decreases entropy, it will be spontaneous at low temperatures. When we're talking about equilibrium, the forward reaction is favored if the products are more abundant, so delta G will be spontaneous. The backward reaction is spontaneous when K is less than 1, so reactants are more abundant. And when reactants and products are comparably abundant, delta G will be equal to 0, but that is going to be a very narrow temperature.